Alright, this video is going to be on logarithms, and it'll be a review from some material that you've probably learned in high school. So we'll start looking at some examples where logarithmic behavior or exponential behavior occurs in nature. And I thought I would start with earthquakes, example from Geology. And here are just some examples of some earthquakes that were significant. The Philippines had one in year 2013, Richter scale 7.1. And if you look on the right here, I just have number of persons that have died as some measure of the extreme nature of the earthquakes. Haiti, maybe remember that one, in the year 2010, Richter scale 7.0, approximately 50,000 people died. Sichuan, China, in 2008, 8.0, that's huge on the Richter scale. Approximately 69,000 people died. In Peru, year before, 2007, you can see another 8.0. I do remember this one in Pakistan in 2005, also around an 8.0, 7.9, 8.0, 30,000 people died. But probably everyone remembers this one, the one that occurred in the Indian Ocean with the huge tsunami. That was right around Christmas. I think it was Christmas Day or Christmas Eve, something like that. And look at the magnitude on that earthquake, 9.0 to 9.3, which caused that huge tsunami, killed 283,000. There's our Northridge quake, 6.8. I was living in Chatsworth at the time. I remember it well, and working at CSUN. And then the last one, if you Google it, you can see that there was one in Shaanxi, China in 1556, and it is assumed to be the deadliest earthquake ever based on the number of people that died. So the Richter scale is a logarithmic scale, and if you see a 6.8 earthquake, in truth it means that the amplitude of the earthquake is going to be proportional to 10 to the power 6.8, which is approximately 10 to the 7. If you look at a 7.9 earthquake, that's going to be approximately equal to 10 to the 8th. So if you looked at the ratio of 10 to the 8 and 10 to the 7, you would see that the 7.9 earthquake is approximately 10 times larger than the 6.8 earthquake. So most people don't understand that about the Richter scale. But an 8 earthquake is about 10 times larger than a 7 earthquake in general. All right, now here is a graph that I pulled from the internet, and here this is not a logarithmic scale. You can see on the ordinate that it's in powers of 10, which implies that there is a exponential relationship there. But 10 to the 4, 10 to the 5, 10 to the 6, and then you see also here that you've got the logarithm of the numbers. So a 3 earthquake, a 4.0, a 5.0, a 6.0, a 7.0 corresponds to magnitude 10 to the 7, and so on. And let me move that up just a little bit there. Okay. So now here's an example from biology, which I made up. So most of my examples here are made up. I'm just sort of illustrating certain trends without any real basis in reality so much. But I chose this example from cell population doubling, and I chose it because in your 102 lab you do an experiment with the coins where you have a bunch of coins and you throw them out, and then ends up being about half heads and half tails, and then you take away the heads, and then you shake out the tails, and it ends up being 50-50 heads, tails again. And so you're watching the population of heads decrease by half every time you throw. So that's kind of an interesting experiment, and you do a graph and so on. So here's an example where at time 0, maybe there's 1 cell, 5 minutes later there's 2 cells, 10 minutes later there's 4 cells. So every time you see 1, 2, 4, 8, 16, 32. So the population is doubling in the same intervals of time, 5-minute intervals of time. And then if you put it in exponential notation with a base 2, 2 to the 0 is equal to 1, 2 to the power 1 is equal to 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16, and so on. So the doubling implies that there's a base 2 there. Now, on your calculator, you could do a base 2 logarithm of the numbers associated with the population. So if you say a base 2 logarithm of 1, then the answer is going to be 0. If you do a base 2 logarithm of 2, then the answer is going to be 1. Base 2 log of 4, the answer is going to be 2. So you're working backwards from, and it's easier to see it in this relationship here. Now, nothing special about base 2. If you look at the rest of this table, there's base 10 and base e as well. So it's certainly possible to take any number. Here's your population on the left. Here, you can take a base 10 log with your calculator easily, and you get the numbers, and then you can take a base e logarithm as well. So the notation, you don't see it so often, log base e. Instead, you use the symbol ln for it. But that's all it is, log base e, where e is a number. So you get a different set of numbers there. All right, and on this slide, you see that if you're just plotting time versus population, so where the population doubles every 5 minutes, you see that there's an exponential increase in the population. Now, if you take the logarithm, base 2 logarithm of the population and plot that, you've got log population versus time, you're going to see a linear relationship. So one of the reasons why we like to do the log plots is that you get a straight line associated with an exponential behavior. And so you can say y is equal to mx plus b, and y in this case is going to be the log base 2 log of the population, and x in this case is going to be the time. So you can see here that the slope of this line is going to be 0.2, and it would be plus b here, but b is going to be 0. So 0.2 would be the slope for that. Move that up a little bit. So it certainly demonstrates the fact that there is an exponential behavior. The fact that you take a logarithm and get a straight line demonstrates that there's exponential. All right, and then here it's the same data, and now we take the base 10 log of the population and plot it. You still get a linear relationship, and y equals mx plus b again. Next slide, take the logarithm, so this is the base e here, the logarithm of the same population versus time. You still get a straight line, and now you have a different slope and a different intercept. Alright, so if you write out the three equations for the line, base 2, base 10, and base e, ln stands for log base e, you see the linear relationship, and even though we had numbers that were close to 0, I went ahead and set them equal to 0, which I think it probably is. If you had enough data points and high precision, you'd see that in all three cases. The time and log x's points go to 0, extrapolate to 0. All right. Now I did mention base 2 and the doubling behavior because it's related to your lab, but in general in lecture we won't be dealing with base 2 at all, so I'm really not going to be too concerned with that. But on the other hand, graphs 3 and 4 and the relationship between log base 10 and log base e, which is the natural log, I'm very much concerned with because we use them interchangeably all the time. So if you do an interesting ratio of the slopes, so if you take 0.1383 and divide it by 0.0602, you get 2.29. So if you did a higher precision calculation of that, you'd end up with 2.303. And so you would see here that the natural log slope is 2.303 times larger than the base 10 log slope. And so if you wanted to actually superimpose the two lines on the same graph, you'd see that all the points would be 2.303 times larger for the natural log plot. So you say the relationship between them is the natural log of the population is 2.303 times larger than the base 10 logarithm of the population. And this is a very general result that the natural log of x is 2.303 times the base 10 logarithm of x. So I put it in red down here. This is something you need to memorize. You need to be really comfortable with this expression because we use it all the time and students ask about it all semester long. It just seems to be a point of real confusion, so might be a good idea to try to remember that now. All right, so in chemistry, we also see exponential and logarithmic behavior. And here I've given the example from kinetics. So this would be a chemical reaction where you have some reactant A decomposing and reacting to form P product. And the graph I'm showing you now is the first order kinetics graph, and you'll understand that once we get more into the chapter on kinetics, but that part doesn't matter so much. But it turns out that first order kinetics is an exponential behavior. And in dark blue here, you see the behavior of the reactant in time. So what this is saying here is that the concentration of the reactant decreases as time goes by. That means as the reaction proceeds, there's less and less of A. At the same time, P is the purple dots, and so the product concentration starts out at 0 and then it grows in and finally becomes constant as the amount of A is depleted. So this would be an exponential decay, this would be an exponential growth. So you can pick either the reactant or the product, and the graph on the right is for the reactant disappearing, so it's got a negative slope here. And you can take the data points for concentration and take the base E logarithm, the natural log of the points, and plot it versus time. And the fact that you get a linear graph tells you that indeed the behavior is exponential decay. And then from this, if you wanted to, you could look at the slope here and the intercept and come up with the equation for the line, and the slope is going to be related to the rate constant for the reaction, and we're going to talk about rate constant as we go through the first chapter. All right, well, those are just some examples to give you an idea of how it works in nature and taking logarithms of an exponential population change, for example, will give you a linear combination. linear result, sorry. All right, now here I've just kind of worked out some numbers, and it might be worth it for you to sit down with your calculator and prove to yourself that you understand this. When we work with logarithms all the time in Chem 102, oftentimes I'll pick a number here and say, well, what is the inverse logarithm of 2.40? Do it in your head. Approximately, what is it? And you come up with, it's approximately 100. It's approximately 10 squared. Not exactly, though. So you should be able to maybe, work with me in the class, just getting a feel for what the numbers are, and then the logs and the inverse logs and so on. So if you start at the top here, logarithm of 1, log 10, log 100, first of all, you can write them in exponential notation, and when you do, you see that the log of the power becomes the answer. Okay, and that's simple as long as it's, 1 times 10 to the 10, 1 times 10 to the 100, 1 times 10 to the 10 to the third. All right, now on the other hand, if they're not exactly powers of 10, in this case it's 2.5 times each one of the powers of 10, then what you see here when you take the logarithm base 10 log is that the powers 1, 2, 3 end up being on the left hand side of the number 1, 2, 3. So when you look at this, the number which is the log represents the logarithm, the number on the left is telling you something about the magnitude. But then the number on the right, notice, is constant, and that's related to the logarithm of 2.5. All right, so we'll see as we go through how to kind of think about these numbers. Also, I got a note here about the number of sig figs. So if this number has 2 sig figs, and you see it clearly when it's written in scientific notation, you have to indicate to the right of the decimal point 2 sig figs. The number on the left is not considered significant because that's related to the power. So there's some examples there. Now, oftentimes students have problems with the inverse logarithm, and basically if you have a number like 2.40, for example, and you need to get back to 250, you want to know where, what the population is or the concentration is if you've given a number in its logarithmic form. So you want to go backwards. And the trick is to figure out on your calculator how to do it, and I wrote out a couple of different ways. It's called the inverse log, also called the anti-log, and then on your calculator, some calculators anyway, you'd push the second button, then the log button, and then it would be taking the second log of whatever the number is you have in there. And so you could try that and make sure that you're getting the right answer. Because sometimes on some calculators it's third rather than second. So other numbers like 2.40 is the anti-log 2.40. You'd press second log 2.40 and you'd see that it would be equal to 250, which is up here. So you want to be able to go backwards and figure it out. Alright, now base E-logs behave the same way, it's just that the numbers are different. The reason why it's no longer base 10, instead it's base E, which is 2.72. And so everything is in powers of E. So you see e to the power 1, e to the power 2, e to the power 3. E to the power 3 is 2.72 to the power 3, which is 20.13. So the log of 20, natural log of 20.13, for example, can be written as log e to the third power, and then you can see how easily you could look at that and say, well, that has to be equal to 3. Alright, so you can play around with some of those numbers there, and same with the inverse ln, the inverse natural log. It's just a sequence that you're going to punch into your calculator. Alright, now we have the laws of logarithms, which most of you are familiar with. The first one I went through in some detail there. The relationship between the base 10 log and the natural log is 2.303. Some of the other ones that students know and remember and like to use, the base 10 log of AB is equal to the log of A plus the log of B, and it's the same thing for the natural log. The log of A over B, or divided by B, is log of A minus log of B. This one we use quite often. Log A to the power n is n log A. And then the next one, log of A, is negative log 1 over A. So sometimes you want to take an inverse of what's in the argument of the log, and when you do, it becomes the negative. You can see that. Now this one is not so much on the logarithms, but I thought I'd throw it in here just for fun. Multiplication division rule, you want to multiply the numbers. 4.8, you're going to divide by 2 here, so it's going to be 2.4. And then here you're going to subtract the exponents to get 10 to the power 2. Just a subtraction, the trick here is to have the same exponents. This is when you're going to be adding these numbers on a piece of paper. So here the power is times 10 to the 0, times 10 to the 0, and the answer would be times 10 to the 0, which is 1. In this case, if you add them together, they have to have the same exponent. So if it were power 1, you'd take 231 here, and you want to make it times 10 to the power 1. So you're going from 10 to the 0 to 10 to the power 1. The exponent gets larger, and the number gets smaller. You can think of it that way. 24, put it in the form of 10 to the minus 1. So it goes from 10 to the 0 to 10 to the 1, and so the exponent gets larger, and that means the number is going to get smaller, and you're going to add them together, and you're going to add the number and just carry down the exponent. And then if you wanted to put it in terms of 10 to the power 2 instead, you're going to make your exponent larger, your number gets smaller, your exponent larger, your number gets smaller, add them up, and in this case you've got it already in terms of proper scientific notation. Alright, so this is the last slide, and you should be able to work out these 3 problems on your own. If you can come up with the correct answers on the right, then you know what you're doing. So that's why I figured that. But also, since I get so many questions on the business of the 2.303, I thought, and I'm using my finger here, I don't have a stylus today. So work out these 3, and then also make sure you understand that 2.303 base 10 logarithm of 2.21 times 10 to the 4th divided by 3.33 times 10 to the minus 2 equals x. Make sure that you get the same answer for x if you set it up that way. 2.303 base 10 logarithm of x over 3.22 times 10 to the minus 5 equals 33. Make sure that you get the same answer for x. And then 2.303 base 10 logarithm of x cubed equals 8.33 times 10 to the minus 2. Make sure that you get the same answer, 1.028 in this example. All right, thanks. See you in class.